For 9 days in June 2026, Earth heard nothing while Parker Solar Probe made its fastest, closest pass alone. After the encounter, NASA confirmed the spacecraft was operating normally. The silence had been planned, but survival was never casual. Parker had swept about 3.8 million miles above the solar surface at roughly 430,000 miles per hour. No human-made object has gone faster. But how do you touch a star with no ground, crust, or shoreline where a probe could land? Here, touch means entering the corona, the sun's upper atmosphere, and sampling its particles and magnetic fields directly. That claim can be tested. The visible surface is roughly 10,000 degrees Fahrenheit. The tenuous corona above can exceed 2 million, and its heating remains debated. Moving outward from the sun should sound like cooling, not heating. Parker was sent into that contradiction because distance had hidden its cause. If millions of degrees were the whole story, no shield should be enough. The missing distinction will become the first test of our mental model. Solar outbursts can threaten astronauts, satellites, aviation, communications, and power grids. The physics near the sun can become a problem near us. That is why this matters. Parker cannot forecast every storm, but its evidence can improve the models behind future predictions. So our question is precise. What can a spacecraft learn inside the sun's atmosphere that instruments farther away cannot, and how do we know? Why bother flying closer? By the time the solar wind reaches Earth, clues to where it began have already changed. Solar wind is a non-stop stream of electrically charged pieces of atoms and magnetic fields, sometimes moving above 1 million miles per hour. Near Earth's orbit, those structures have stretched, collided, and mixed. Measurements remain valuable, but many signatures of origin are no longer pristine. Think of river water after tributaries blend. The comparison stops at mixing. Solar wind is plasma, electrically charged gas spreading through space, not between riverbanks. Sampling that plasma early preserves source clues the long trip would blur. Nearness protects evidence. In 1958, physicist Eugene Parker proposed this persistent outflow. His namesake spacecraft carried the question toward its source. Earlier missions studied the wind from afar. Parker sought what those measurements could not recover after the journey. Parker launched on August 12, 2018, aboard a powerful Delta IV Heavy to reach those fresher clues. It is like moving toward the center of a spinning carousel while already circling its edge. First, change your sideways motion. Space has no carousel floor. Under gravity, Venus encounters repeatedly reshaped Parker's orbit, bringing each solar pass closer. Each return carried Parker deeper into wind that still remembered the conditions that launched it. The route served the evidence, reached the wind before travel and mixing erased its source pattern. Why distinguish temperature from heating? It explains how Parker can enter the corona while its electronics stay near room temperature. Temperature tells how fast particles move. Transferred heat depends on the energy they deliver when striking an object. Coronal particles move extraordinarily fast, but are extremely sparse. Few impacts transfer less heat than temperature alone suggests. A hot oven can be safer briefly than dense boiling water. The corona is neither. Intense sunlight means sparse plasma alone cannot protect Parker. That barrier is an 8-foot thermal shield. Carbon-carbon faces around 4.5 inches of lightweight carbon foam. Large in area, it is mostly insulation. Its sun-facing surface is white ceramic, chosen to reflect as much incoming energy as possible. The shield does not defeat heat by thickness alone. Pre-flight models allowed the front to approach 2,500 degrees Fahrenheit, while the spacecraft behind it stayed near 85. Orientation creates two thermal worlds. At the 2026 close pass, models estimated about 1,700 degrees on the shield. Stable temperatures behind it showed no sign of thermal protection degrading. Near the Sun, Parker retracts most solar arrays into the shield's shadow, leaving only a small power-producing area exposed. Clean, pressurized water circulates through the solar array cooling system and carries heat toward radiators. Ordinary water becomes mission-critical cooling hardware. Earth cannot rescue a bad pointing decision in real time. Sunlight takes about 8 minutes to travel one way. Parker must protect itself. Sun sensors watch the edge of the shield's shadow. If sunlight reaches one, onboard software corrects Parker's pointing direction without waiting for permission. Now predict the failure chain if the shield tilts. Sensors see light, software reacts, and every protected component depends on that correction arriving first. How would Parker prove its location? 4 instrument suites test the same event through fields, pictures, ordinary particles, and high-energy particles. Imagine 4 investigators recording force, scene, crowd motion, and fast outliers. Unlike witnesses, these are calibrated sensors with overlapping physical measurements. Fields tracks how electric and magnetic forces change from moment to moment. Abrupt changes can reveal shocks or places where magnetic paths rearrange. A magnetic field has no color or glowing outline. When we draw its direction later, that geometry will represent measurements, not visible scenery. WISPR is Parker's only imager. It photographs broad coronal structures, ejections, jets, and streamers before the spacecraft flies through them. The heat shield blocks most direct sunlight. Internal baffles absorb or redirect stray glare that would otherwise bury the corona's faint signal. First, WISPR sees a structure approaching. Later, other sensors measure it at the spacecraft, joining large-scale shape to local physical detail. SWAP counts the wind's electrons, protons, and helium particles. It measures how fast, dense, and hot the local flow is. Now wind is no metaphor. At each moment it becomes numbers for particle abundance, motion, and temperature that can change across a boundary. IS letter 298 follows the fastest electrons and atomic particles. Their type and energy preserve clues to where they gained speed. An image locates the structure, fields measures local fields, SWAP measures bulk flow, IS letter 298 checks energetic particles. Their agreement is the power. Why learn the boundary at all? It lets us test the phrase, touching the sun, instead of trusting a distance record or a headline. On an airport walkway, you can turn back until the belt moves faster than you can walk and carries you one way. Plasma is not a walkway. The Ulfvén critical surface is the return test. Can a magnetic signal reach the sun, or will outward wind sweep it away? The Ulfvén critical surface is where outward wind becomes faster than any returning magnetic signal. It shifts, and it is not a shell. Estimates placed it between 10 and 20 solar radii, each the distance from the sun's center to its visible edge. Its shape remained uncertain. A close distance could not prove entry by itself. Parker needed the predicted combination of field strength, particle flow, and magnetic control. On April 28, 2021, during its 8th flyby, Parker reached those conditions at about 18.8 solar radii, roughly 8.1 million miles above the surface. Parker found strong magnetic control and particles still connected to the sun. Those predicted signs meant it had entered the corona. During that passage, Parker moved in and out of those conditions several times. A smooth spherical boundary would not behave that way. The Ulfvén surface has spikes and valleys that track solar structures. Inside is a physical state, not one universal altitude. Inside one tall coronal structure, particles slowed, conditions quieted, and sharp magnetic flips became scarce. A genuinely different environment had appeared. Their magnetic fields controlled particle motion. That coordinated change, not a photograph of an invisible border, was the decisive evidence. Which proves more, a distance record or fields and particles changing together as theory predicts? The second turns a location into a scientific crossing. Those magnetic flips became the next clue. Why study them? Their pattern might reveal where the young wind began and how it escaped. A garden hose can form a U-shaped bend while water moves forward. The hose is only a guide. Magnetic fields are invisible. A switchback is a quick U-turn in measured magnetic direction, often paired with a plasma burst. No glowing kink was photographed. During early passes, Parker traced one slow wind sample to a small region near the sun's equator, where magnetic paths opened outward. The switchbacks arrived with brief plasma jets. Instead of a smooth breeze, Parker was crossing bursts with several properties changing together. Like minerals in tap water hint at its source, helium in each burst offered another source tag. Solar wind is not household water, so helium was not enough. Images and magnetic models help trace one source near the visible surface. On a closer pass, fast wind arrived in packets lasting about 2 hours instead of roughly 10. Some ions, charged pieces of atoms, in those packets carried unusually high energy. The source pattern recorded acceleration as well as shape. Timing, helium, magnetic flips, solar images, and models converged on structured source regions. Different clues were pointing to the same birthplace. Sought the evidence. Parker measured particles and fields, models traced them to the sun, simulations would test a cause. Finding the birthplace did not explain the energy. To predict the wind, scientists needed a mechanism, not just an address. Picture a fenced side road joining an open highway. Trapped traffic escapes. Magnetic paths are not roads, and they can release stored energy. Interchange reconnection means closed magnetic paths join open ones, releasing plasma. Simulations tested whether this could create Parker's measured bursts. Simulations matched important features, and measured energy could power this fast wind. That supports the mechanism without making a model an observation. The result does not explain every solar wind or the corona's full heating. Slow wind still has several plausible sources. During the December 2024 record pass, WASPR captured the closest images ever made from within the solar atmosphere, about 3.8 million miles above the surface. The images resolved a vast sheet-like region where the sun's magnetic direction reverses. Invisible magnetism gained a visible plasma context. WASPR also caught several coronal mass ejections, huge eruptions of solar material colliding in high resolution. Near the source, storms were not isolated bubbles. When ejections merge, their trajectories can change. A forecast based on each eruption alone may miss the path created by their interaction. Mergers can accelerate particles and mix magnetic fields, changing risks to spacecraft and people. Close images now constrain that evolving physics. Parker joined close images with local measurements, preserving clues distance would blur. Nearness turned a picture into a test of cause. The full coronal heating budget remains open, and slow wind origins are not settled. Reaching the laboratory transformed the questions, it did not end them. For any invisible frontier, ask, what defines it, what should instruments detect, what changed, and what remains uncertain?